Thanks for coming to our talk. Hi, I'm Calvin Liu, and I'll be presenting on behalf of all of our authors on our work, Time Waits for No One, Analysis and Challenges of Temporal Misalignment. Something that has been well studied is that language use changes over time. For example, new entities or events get introduced or become more prominent over time. And how we react to or use certain words can change. For example, words can be reclaimed by minority groups, or certain objects can become more polarized due to events. However, the way that we train our models don't necessarily reflect this. Oftentimes, we train a static model on data from one time period, but deploy or evaluate it on data from another. In our work, we call this phenomenon temporal misalignment. This is actually a problem that's often referenced by our friends in industry, and there it's called domain or concept drift. Our goal in this work was to thoroughly quantify how our models are affected by temporal misalignment for a variety of domains and tasks. Specifically, we want to see how much temporal misalignment affects downstream task performance of systems built with large pre-trained language models. As an overview for the talk, we'll go through the typical NLP pipeline and identify the places that temporal misalignment can possibly occur. In pre-training, where it is computationally expensive, and fine-tuning, where annotation can be expensive. We introduce our dataset, which, to our knowledge, is one of the first comprehensive collections of temporally organized downstream tasks across several domains. And then we go over our problem setup and results from our fine-tuning experiments. We find that models can see a considerable amount of degradation, and the levels of degradation ultimately depends on the task that you care about. We also investigate how well domain adaptation to a particular time period would be in curbing model degradation over time. We find that simple forms of pre-training could not overcome deterioration due to misaligned labels. We perform our study on models with the pre-trained DAPT fine-tuned paradigm. Just as a brief reminder, if we have a particular task that we care about, like whether a Twitter tweet came from a US Democrat, we usually take our favorite pre-trained language model, trained unsupervised over a large volume of text, and use that as the base of our model. Optionally, we can do an additional, smaller pre-training step called domain adaptation, or DAPT, on text from the same domain as our end downstream task. So in our running example, we would be adapting to Twitter tweets. This is still relatively cheap. While the data is restricted to the domain that we care about, it is still unlabeled. Finally, we use the labeled data to fine-tune our language model for the task that we had in mind. This gives us the resultant model. So the question is, where in the pipeline can our models be affected by temporal misalignment? We suggest that it might be where updating our models is expensive. On the left, training these models can mean many hours of compute. As an example, GPT-3 reportedly costed several $1 million to train. And this isn't exactly feasible for most researchers. Prior work has studied the effect of language change when pre-training from scratch as well. On the right side, annotating new data can be costly and require a lot of human effort both in performing the annotation and designing the schema. Moreover, current NLP culture does not update their datasets. Most datasets are static once published. We'll focus on the fine-tuning steps in our analysis of temporal misalignment. Domain adaptation is interesting since it is a cheaper middle ground between the two. Unlabeled data is cheap, and additional pre-training is much cheaper than training from scratch. We also investigated how useful it is to do temporal adaptation, where we adapt a language model to a target time period. We then ask 4 research questions. First, how does misalignment affect downstream task performance? Is it an important thing to note? Or do our models, empowered by large pre-trained models, generalize well to temporal misalignment? If it does have an effect, are all domains and tasks treated equally? Concurrent work has really been only limited to one or a few domains or tasks, but we might expect language in something like food reviews to be more static than political tweets. Does misalignment affect upstream language modeling for different domains? And finally, can we use domain adaptation, which we dubbed temporal adaptation before, to adapt our model to a target time period in order to mitigate the effects of temporal misalignment? We can split these questions into 2 groups, one pertaining to fine-tuning with labeled data, and the other more so about the temporal adaptation steps. I've color-coded them as purple and green accordingly, and we'll do them in order. But before we start with the fine-tuning experiments, we first introduce our task and domains here. We use 4 domains: Twitter tweets, scientific documents, news articles, and food reviews. For each domain, we compile up to 3 different tasks. These are mostly classification tasks with one exception, news summarization. Instructions for how to obtain the data and preprocessing scripts can be found in our GitHub repository. As an aside, we selected the Yelp dataset, which only includes data pre-COVID as kind of a control. Unlike the other tasks and domains included, we don't expect much change here. We don't think that the way that people will talk about food is going to change much over time. To approach these questions, we design our experiments as follows. We split our datasets for each task into equally sized time periods. These time periods can vary from something like yearly, like 2014 to 2020, or binning several years together. So something like 2000 to 2004 would be a bin, and 2005 to 2009 would be another. Then for a particular time period t, we train a model for that task with training data from t. Afterwards, we take the trained model and evaluate it over all time periods and compare how well it did on all the time periods. And we keep doing this train and evaluation step for each time period so that we have a model for each one. So you can imagine that we end up with this n by n grid of scores where one axis is the train times and the other is the evaluation times. Before we move on, we should talk about an additional metric we use to quantify model degradation over time. We report F1 scores for classification and Rougeol for summarization, but you can imagine that reporting these for so many models and over so many evaluation points can be messy. What might be useful is a singular number to make analysis of this phenomenon a little bit easier. An idea might be, for a fixed evaluation time period, plot out different models and use the slope to quantify degradation. This idea leads to a simple metric we introduced called the temporal degradation score, or TD score. The basic premise is that we want to fit the deviations, which we defined as a modified difference between the misaligned model and aligned one to a line. The slope then describes how much degradation we expect for each year that we are misaligned from the evaluation time period. And more details on this can be found in our paper. Now on to results. Here I've plotted the raw F1 and RL scores of a subset of our tasks. The numbers themselves aren't super important here. What are the colors you see? Darker oranges and browns indicate better performance. So this is kind of what we might expect for the left three plots. The diagonals, where the train and test are temporally aligned, are the darkest colors, indicating the highest performance. Moreover, we generally see that the more and more you are misaligned, the worse your performance degrades. The exception seems to be our Yelp start prediction task, where it looks a little bit random. This is kind of expected. If you remember when we first introduced the task, we included Yelp as a kind of control. We didn't expect to see much change here. Here we plot the TD scores of all of our tasks. We see quite a bit of variance, but notably, some of these are quite large. In the most egregious case, we see over 7 points of deterioration for each year in political Twitter affiliation, and just under 6 for news publisher classification. Even in the case of summarization, 1 point drop in Rougeol can be quite large. This answers the first question. It does seem to matter in a lot of cases. In fact, for a majority of our tasks, the TD score for each task was above 1, so we see at least 1 point of degradation. For the second question, the plot suggests, yes, it varies a lot. We pointed out earlier that the food reviews domain changed little, and that's also reflected here in the TD score. More surprisingly, however, is that two tasks on the same domain can be drastically different. Entity typing on Twitter seems to be relatively robust. However, political affiliations is the most sensitive to temporal misalignment. So for our two questions regarding fine-tuning, we see that temporal misalignment can have a large effect on downstream tasks, and that the degree of deterioration depends on both the task and the domain. So now we move on to our questions regarding additional pre-training or domain adaptation. In our case, we are adapting to a target time period. First, we want to see if misalignment affects upstream language modeling. We want to emphasize that we're going to be taking a step back to focus on language modeling perplexity rather than downstream applications, at least for now. And we found that for all of 4 of our domains, yes, it does, which is consistent with what other recent work has found as well. So here on the right, we have a plot of the perplexities of our language model where lower is better. This is flipped from last time. This time, lighter colors are better. Again, don't worry too much about the numbers, rather the gradient is more important. We notice that generally, language modeling performance gets worse the further we evaluate away from the training time period. These imply that temporal adaptation is helpful for language modeling. Even Yelp, which we included as a kind of control, sees improvement with temporal adaptation in upstream language modeling. And further details about this part of our experiments can be found in our paper. So now that we know that adaptation helps the upstream tasks, we're going to go back to downstream tasks and ask, is that improvement enough to mitigate the effects of temporal misalignment in downstream applications? And this would be helpful since annotating new data would be expensive, but domain adaptation is relatively cheap. It uses unlabeled data, and we aren't training a full language model from scratch. The experimental setup is a little different from the one before. Instead of looking at all of the time periods, we just do temporal adaptation for the earliest and latest time periods. This gives us 3 models, 2 that are adapted, and 1 that has no adaptation. We then fine-tune and evaluate each of the 3 models on the earliest and latest time periods. If adaptation does not help, then we would expect there to be no significant difference between the performance of the 3 models. Unfortunately, that does seem to be the case. Here I have one example task, political affiliation classification, on 2015 Twitter. We see that for all 3, the results are very similar, and these results here generalize to all the other domains and tasks. Temporal adaptation does not seem to mitigate the degradation from temporal misalignment. There does not seem to be a suitable substitute for getting new label data. So to sum up, we looked into how temporal misalignment can affect model performance in downstream applications for a variety of tasks and domains. We found that models, more often than not, do not generalize well temporally and can suffer severely in some cases. Moreover, the level of deterioration depends on the domain and the task definition. Even 2 tasks on the same domain can degrade at differing rates. We also look into the effectiveness of temporal adaptation to help curb model degradation over time. While it may help with upstream language modeling, it doesn't seem to help for downstream applications. At least for now, we can't get away from this problem without updating our labels as well. So thanks for listening to our talk, and we invite you to read our paper. And whether you're virtual or in person, feel free to chat with us about this work.